In this lecture, we're going to finally learn how to compute the fundamental group of new spaces. So up to this point, we know how to compute the fundamental group of a contractible space, and the space which has the same homotopy type as a circle. So we know what a contractible space is. That's a space that can be collapsed down to a single point. There's a homotopy, a continuous deformation of the space which collapses the space down to a single point. For example, any convex set is contractible, and as a result, the fundamental group is trivial. Whereas the circle, its fundamental group is isomorphic to the integers, and any space which has the same homotopy type as a circle will therefore have the same fundamental group. So for example, the punctured plane, as we saw, has the same homotopy type as a circle. But there are, of course, spaces that have a very different homotopy type. And as a result, we need methods that allow us to compute the fundamental group of spaces more generally. And the main theorem that allows us to do that is called the Seifert von Kampen theorem. It's named after two people. It might be confusing because it seems like one name, but it's two people who independently discovered this theorem in topology about the fundamental group. And basically what this theorem does, it is a theorem that expresses the fundamental group of the space in terms of simpler subspaces. So the idea is, if you can break your space into subspaces and you know what the fundamental group is on those subspaces, then it is possible to use that information to find the fundamental group on the entire space. And that's what we're going to discuss. Now, I should say that the original Seifert von Kampen theorem is probably stated very differently from the way we're going to state it in our lecture, because it's a theorem that probably goes back to the beginning of the 1900s, early 1900s, and a lot of the stuff that we've discussed, especially the last two lectures, is a lot more modern. So we're going to give a modern restatement of the theorem that hopefully makes it easier to understand. And then you will appreciate the two previous lectures that we had on combinatorial group theory, and you will see how nicely it fits together with everything we've talked about up to this point. So here is the theorem, and what we'll do in this lecture is we will state what the theorem says, and then we will give a proof of the theorem, well, almost a proof of the theorem. There's going to be a small technicality that is very tedious, and justifying that technicality is the longest part of the proof. But we will present the main idea behind the proof and how it works. And so today we'll just state the theorem, we'll make sure we understand what it says, then we'll give a proof, not counting that small technicality so that we do not waste an enormous amount of time on it. In fact, Moncrief spends multiple pages discussing that technicality. And then the lecture after this one, we will actually see how this theorem is used to compute the fundamental group of various spaces. But today we should at least state what the theorem says, and then next time we'll get to use it and you'll see the power of this theorem. So here is the theorem. Let X be a space and P is a point in X, and let U and V be open subsets of X containing this point. And we're going to assume that U, V, and their union, their intersection, I should say, are path connected. So we're assuming that these are path connected open subsets and their intersection is path connected. By the way, the intersection of two open sets does not have to be, it does not even have to be connected. You can have something like this. So something very simple. As you can see, that's the intersection. It's not even connected. So the assumption here is you have open sets. The intersection of two open sets is an open subset of X. And all of these open sets, they all contain P, and they happen to be path connected. Path connected just means that between any 2 points in those subsets, you can find a path within that set that connects those 2 points. Okay, so here is what we do next. So we have the following inclusions. We have the inclusions, the inclusion maps. So we have the inclusion map, let's call it I, that maps U intersect V into U. And we have J that maps U intersect V into V. So these are just the inclusion maps. These are the maps where every point is mapped to itself. So those are the inclusion maps. And we also have this inclusion map, let's call it I prime, that maps U into X. And we have J prime that maps V into X. So we have all of these inclusion maps. And now let's pass to the fundamental group. So recall, the fundamental group is a functor. So anytime you have maps, continuous maps between spaces, the fundamental group induces a homomorphism between the fundamental groups of those spaces. So these are going to be, so let me redraw this picture for you. So this picture will look like this. We have U intersect V going into U. This is V, like that. And then, yeah, and then you have X over here. So this is I, this is J, that's I prime, this is J prime. This diagram commutes. This diagram commutes for a very simple reason, because if you pick an X, so if you pick an X in here, so if you pick something in here, X, what does the I do? It sends X to X, because it's just the inclusion map, and I prime sends X to X again. That would be the same way if you go down here. So it's quite obvious why it commutes. So now if you apply the fundamental group functor, you're going to get a diagram that looks like this. You're going to have pi 1 U intersect V at P, and then you have this mapping, which we call I star, that's the induced mapping, pi 1 of U at P. Then you have I star prime. This is pi 1 of X at P. This is J star, pi 1 of V at P. And we have a mapping going like this, which we call J prime star. And this diagram also commutes. So this diagram commutes as well, for the simple reason because the fundamental group preserves commutative diagrams. That's one of the properties of the fundamental group functor that we've talked about. If you have a commutative diagram of topological spaces and you apply the fundamental group to the diagram, then you get a diagram of groups and homomorphisms between the groups, and everything will commute. I also should say it's important that usually when you're doing things like this, you do have to check that the base point is going into the correct positions, in which case it is, because all three of these open sets, they contain the point P, and because these are inclusion maps, the point P is always being sent to itself. So P is sent to P, so this is correct. So that's a commutative diagram of groups. Now, if you look at this, this should remind you of what we call the push out. This is the push out. So we're saying that this fundamental group is the push out because you can find a pair of maps, homomorphisms, that commute with these two. And to be a push out means it's universal. It's the optimal group. It's in some sense the smallest group through which you can push out this diagram. Okay, so let's say what the theorem says. So then pi 1 xp is the push out. It's the push out. Or if you prefer, you can also call it the fibered coproduct. So that's what the Seifert von Kampen theorem says. This is not the way it was originally stated. I believe the original treatment of this theorem, it explained how to express this group using generators and relations. So the original statement of the theorem said that if you knew the generators and relations for all of those, how you can get the group presentation for this. But I think the much better way, a way that makes a lot more sense and is more straightforward to prove, is to show it satisfies the definition of a push-out. And then our previous lecture where we talked about products and coproducts and how they can be computed from the group presentation will then be appropriate, and then we'll be able to take advantage of that and compute these fundamental groups. I do want to make a warning. We've said this warning before, but just something to keep in mind before we go on to prove this theorem. So here's a warning. Warning. Let's say it does not really matter. Let's say A. I do not want to use U and make you think that it's an open subset. So let's say A is a subset of X, and they both contain some point. And say we have the inclusion map from A into X, which maps X to just itself. That's a continuous map. So we get a map on the fundamental group. So the fundamental group of A at P is being mapped, we call this I star, is being mapped to pi 1x of P. So in general, this homomorphism, I star, is not injective. It could be injective, but it's not guaranteed to be injective. Now, how is I star defined? And recall that I star is defined as follows. So in order to define this induced map, you have to say what it does to a homotopy class. So you're going to take a homotopy class of a loop in A. So if theta represents a loop, then I star of that loop is just I composed. You just do it by composition. So, but I compose. So the reason for this is because theta is a loop. So theta is a map from I to X. I'm sorry, theta is a map from I to A, because theta is a loop in A. So it's a mapping from I into A, and the inclusion mapping is a mapping from I into X. So if you do the composition, you get a mapping from I into X. So to put it quite simply, if theta is a loop in A, it is also a loop in X, because A sits inside X. You can basically enlarge the codomain because A is sitting inside X. And then you just are thinking of this as a loop of X. So this is, of course, just itself, because if you compose with the inclusion, that's like basically composing with the identity, so nothing happens. And when you look at something like this, it appears that it's like the identity mapping. It's mapping a homotopy class to itself. But the part you have to be extremely careful about is that this is really the homotopy class. That's the homotopy class in A. So we can put a subscript here to indicate that this is the homotopy class in A, whereas this is the homotopy class in X. And these can be very different. So to use this example that we've used this example before, but it's a good example to keep in mind, it's quite simply this, that the circle, there's an inclusion into the complex plane. But when you look at the fundamental group of the circle at some point, let's say 1, and you have this map I star going into the fundamental group of the circle, this is, of course, the trivial group, and this is the integer group, and this is not even close to being injective. This is the worst possible type of mapping where everything gets sent to a single point. It's the extreme opposite of being injective. And the reason for this is because if you pick a homotopy class in here, right? So let's say theta is the loop that's given by the following function, then the homotopy class, so when you look at it as a homotopy class in S1, this is not trivial. But when you look at the very same loop as a loop in the complex plane, then it is trivial. Because this loop on the circle, right, so here's your loop on the circle, when you look at this, when you think of this loop as sitting inside the complex plane, then suddenly you have all that space in the middle, and then this loop can be contracted down to a single point, and so it becomes the trivial, this becomes the trivial homotopy class. So that's what's happening here, that just because it looks like the homotopy class of theta is being mapped to itself, that does not mean this is an injective mapping. In actuality, it's mapping a homotopy class into a larger space, and in the larger space, the homotopy class may become trivial. So this is the part where one has to be extremely careful with, that it might look like an inclusion, but it is not necessarily an inclusion. So just bringing this up here so that maybe it will help avoid some confusion that perhaps some people might have as we're discussing this proof. Okay, so this is what we have here. So what do we have to prove? Okay, so here's what we have to prove. So to show that pi 1 xp, so we want to show that that's the push out, or the fibered coproduct, depending what terminology you like to use. So you want to show this is the push out, right? That this is the claim. The claim is the fundamental group is the push out of this diagram of groups. You have these three groups, right? So these are like the three given groups, and the fundamental group that you're trying to compute is the push out of this diagram. And these induced inclusion maps, which are not necessarily inclusion maps anymore after you look at the corresponding map between the fundamental groups. That's why we say the induced inclusion maps and not inclusion maps, that they form a push out, that it satisfies. You can see this is commutative. So this is a commutative diagram for reasons that we've said before. These commute, and this is the optimal group that will commute with this diagram. So to show that pi1 xp is the push out, so maybe it would be helpful to write it like this, is the push out of, and whenever you talk about the push out, you always talk about the push out of some diagram. So I'm going to just redraw this diagram again. I'm going to be sloppy. I'm going to hide the base point just to save writing space. Maybe we can even write it like this. Let's write it perhaps pi1 u intersect v. Then we'll write it like this, pi1 u pi1 v. We're going to suppress a lot. We're going to suppress these inclusion maps, these homomorphisms. We'll suppress the base point, so we'll just write this. So to show that the fundamental group is the push out, so I forgot to write the word, is the push out, is the push out of that diagram, we need to show, so by definition, so this is the definition of the push out. The push out is the optimal such group. We can see that the fundamental group commutes. So if you put the fundamental group here, it commutes with this diagram. We have to show that if you find another group that commutes with the diagram, then it's larger, quote unquote, larger than the fundamental group. The fundamental group in some sense is the smallest out of all of them. It's sort of like the supremum. It's the optimal one. It's like the least upper bound. So by definition, if there is another group H such that it commutes with the diagram, so that would mean that you have, so I'm going to redraw the diagram again, pi1 of u, pi1 of v, and we're going to put, let's use a different color, H. So we're claiming that if you can find another group H that fits into the diagram, that pushes the diagram out, let's call these maps F and G. So if you can find maps, or maybe not call them F and G, let's call them something else. So we have I, J, maybe we should call them K. Let's call them K and L. So let's say there's a mapping K and there's a mapping L. So if there is another group through which you can push out the diagram, right? You can push out the diagram from that group. And so that K and L commute with this diagram, then there is a unique homomorphism. So there's a unique homomorphism. So let me draw the fundamental group in here, pi1 of x. So we're claiming that this is the optimal way to push out the diagram. So if it's the optimal way to push out the diagram, then this is sort of the supremum. There's a mapping from pi1x into H. There's a unique mapping from here into H, which makes the diagram commute. And there's a unique homomorphism, maybe you can call phi or something. Let's call it H maybe. Let's actually call it H. Unique homomorphism H from pi1x into H, which commutes with the diagram. So there's two claims here, uniqueness and existence. So we're saying there exists a homomorphism. You can construct a homomorphism from the fundamental group of X into this arbitrary group H. By the way, this group H, the reason why these K and L over here, they do not have the star decorations. You see over here we have these star decorations, but there's no star decorations on K and L, is because this is just an arbitrary group. It has nothing to do with topology. Like, we're not saying that this is a group coming from some topological space, and these maps are the induced maps coming from some continuous maps between topological spaces. This is just general group theory. The reason why we have stars over here is because these maps are coming from topology. We had topology here, and these maps came from the topology. Whereas this H, that's just an arbitrary group from the group theory universe. It might have absolutely nothing to do with topology, and these homomorphisms might have nothing to do with topology. That's the reason why we're not putting those star decorations on them. So we have this arbitrary group through which we can push the diagram out, and we want to show that pi 1 of x is the optimal one, that any push out through H factors through the push out of the fundamental group. So this is what we have to justify. So we're claiming that there exists a homomorphism and it is unique. There's only one way to do it. So we're going to kind of do both at the same time. So in the course, so as we write the proof, so as we write this proof, pay special attention to the fact that the choice, so that the choices are being forced on us. So such a map must be unique. So as we write the proof, you will see that we will be required, if we want to be able to satisfy all of those commutative diagram properties, certain things will be forced upon us. And it's those forced choices that will make it unique. So the uniqueness will follow from the forced choices that, I mean, it's kind of, I guess, ironic to call them forced choices, but you get the idea that we're not really going to have much of a choice in how to construct that homomorphism. So that's what we're saying. Okay, so in order to construct a homomorphism, what do we need to do? So here's the way it works. So to construct this homomorphism, H from pi 1 x p into H, we need to pick a homotopy class of a loop. So theta is going to be a loop, okay? So this is the homotopy class of a loop. So theta is a loop. So theta is a mapping from the closed unit interval into X, because that's the definition of a loop. It's a mapping from the closed unit interval into X, and the value of it at the endpoints are equal to that point P. That's just the definition of a loop. So we need to pick a homotopy class of a loop and define H of theta. We need to say where it goes. And I'm going to just add a little bit of a decoration here that I think will be helpful. Because this is a homotopy class in X, let's just decorate it with this X. So that's just a homotopy class of theta in X. So we have to define where H goes. We have to define where this is being mapped to. That's the question. Where does this go? How do we define it? So we're going to do this in various stages. So we will do this. So we will define H, right? So we're trying to define a mapping, right? We're trying to construct. So to construct a mapping means given something in the fundamental group, which by definition is a homotopy class in X of a loop. So this is a loop. We have to say what H will do to that homotopy class. Where is it being sent to? So we will define H in various steps. So first, we will assume that theta is let's call it a pure loop. So what is a pure loop? A pure loop means, i.e. theta is entirely contained in either U or V. That's what we mean a pure loop. It is sitting inside U or V. So let's just recall what U and V are in the statement of the theorem. In the statement of the theorem, we're covering X by a union. Oh, I forgot to say something, right? I should have mentioned something. I guess I should add it over here. Containing X, and X is the union of those two sets. So this is a cover, right? This is an open cover for X. X is a union of two open sets. It is possible, by the way, to generalize this theorem to a collection of 3 open sets or even an infinite collection, but let's not go overboard. Just doing it for 2 is generally good enough. So X is a union of two open sets. Okay, so that's what U and V are. So so let's draw a little picture here. I think this will be helpful. So you have a picture. So here's like an open set U. Here's another open set V. Now they happen to intersect, and the point P is a point in their intersection. We also assume that U, V, and the intersection are all path-connected spaces. So what we're saying is that we have a loop that is located at this point P. So let me draw some pictures for you so we get an idea of what's going on. You see, here's a loop. This is what we call a pure loop, because this loop is completely contained in V alone. Now you can also have a loop that goes like this. So that would be theta, that's your loop. It is entirely contained in U. It is also possible that it's contained in both. Okay, so that would be a loop that is actually contained in both. But by definition, it is a pure loop. A pure loop means it is either in U or in V, in one of these two. So that's a pure loop. Now, an example of a loop which is not pure is, let's say it goes something like this. So here's a loop. As you can see from this picture, this loop, part of it is in U, but not entirely, and part of it is in, so part of it is in V and part of it is in U, but the whole loop taken together does not sit entirely in one of those two sets. So that's what we have there. So if theta is a pure loop entirely contained in U and V, so then it means theta is either a mapping, so it's a mapping either into U or it's a mapping into V, right? That's what we're saying. In general, theta is a mapping into X. It's a loop in X. But when it's a pure loop, it is either a mapping from I into U or it's a mapping from I into V. So one of these two is going to be satisfied. So thus, okay, so then what would this mean? So then the homotopy class of theta at X, it can be as, so this is the way you can write it. You can write it as the homotopy class of X in U, and then you're going to map it using I star, or it's the homotopy class in V, and you're just going to map it using J star, right? So those are the maps we had in the beginning. So maybe instead of scrolling all the way back up again, maybe we should just redraw these maps down here so we see them. So here we have pi 1 of U intersect V. I'm going to drop the point because I want to be sloppy and save space. And then we have this map. Oh, actually, that's incorrect. Yeah, that's incorrect. Actually, no, that's fine. So we have this. We have pi 1 U intersect V. It's being mapped by something we call I star, pi 1 of U. And then this is being mapped by what we call I star prime. So this is pi 1 of X. This is being mapped by J star into pi 1 of V. And then this one is being mapped by J star prime. Okay, so if theta is a loop in U, then that means the homotopy class of theta in U, the homotopy class in U, it's in here. But you want to get something in here, right? This is an element, right? This is an element of the fundamental group. So, but what you can do is, this is what we were saying earlier, if theta is a pure loop, then if you consider the homotopy class of theta as a homotopy class in U, then I star, by definition, maps the homotopy class in U. By definition, it maps it to the homotopy class in X. So you can express this homotopy class as a mapping of this. So this should be I star, by the way, right? So this mapping is I star. So this should be I star prime. I star is this one, but this is the one with the prime. So I should include the prime there. So this or this. So one of those two. Okay. So the picture is we've chosen a pure loop, right? So we've chosen. Yeah, I definitely need to draw a bigger picture. This is just not going to make any sense. So let me redraw a much larger picture. Pi 1 U intersect V. This is I star, pi 1 of U, J star, pi 1 of V. This is pi 1 of X. This is I star prime. This is j star prime. Okay, so we're saying that we're picking a homotopy class. We're picking something, a homotopy class in X. Now, if theta is a pure loop, then that means it can be written either like this or like this, one of these two. So it's the image of either this one or this one. Okay, so let's say it's the one on the left. So then you can find theta. So then this homotopy class is being mapped by I star prime into that homotopy class. So this one can be pulled back. Now, here's the way this map H is going to be constructed. In order to construct this map H, we have to explain how this, we have to define what H is doing. So given this homotopy class, we have to explain where it is being mapped to. How do we map it into H? So in our picture, let's say H is located all the way out here. This is H. And H, we said, has two mappings. One of them is called K, and the other one we're calling L. And these mappings compute with this diagram. And we're trying to construct a mapping. Let's use a thinner color. We're trying to construct a mapping. Maybe we should do it by a dotted line. We're trying to construct a mapping, a homomorphism called H, that will take this loop and send it into H. So how does one do something like this? Well, you're going to use the commutative diagram to do that for you. Let us suppose that this is a pure loop. If it is a pure loop, then it means you can either pull it back here or you can pull it back here. It's going to be the same idea, but if it's a pure loop, it can be pulled back by using either I prime or j prime. So let's say you can pull it back using I prime. So when you pull it back using I prime, you already have that map K. So the way you define the image of this in H is by using the commutative diagram. Notice the choices are being forced on you. If you want this diagram to commute, that's the way you have to do it. There's no other choice. If this one can be pulled back, okay, then in order to commute with the diagram, the way it gets mapped by H should be the exact same way it gets mapped by K. And then you then define that H maps this homotopy class by the rule that you're going to apply K to this homotopy class. Now, K is given to you. That's a given homomorphism because you're making the assumption that you're given a group which pushes the diagram out. So in particular, there's these two homomorphisms, K and L, that are compatible with the morphisms that you currently have. So the K and L are given to you. You do not have to construct the K and the L. It's the H that you have to construct. And the way you map this homotopy class into H is you're arguing that if it's a pure class, then that means it can be pulled back. And if it can be pulled back, then the correct way to map it into H has to follow the same arrow as this one because of the commutative diagram. And then H of this is defined to be K of whatever that is. Okay? And then you define, and then, we then define, and this is forced. Notice that this is forced. There's absolutely no choice in this whatsoever. So this is what we're saying by uniqueness. This is being forced on us. There's only one way to do it. So then we define H of this homotopy class X. That was mistype. It's the homotopy class and then subscript X on the outside. We then define it to be equal to, so based on this picture, you will either use the K map or the L map, depending whether it pulls back like this or it pulls back like that. So either you're going to write this homotopy class either in this form or in that form, and then depending which of the two it is, you will then use one of those two maps. So then it's going to be equal to K applied to theta of U, or L applied to theta as a homotopy class in V. So that's the way you define H on a pure class. Now, we have to check something. So there's a check that needs to be made. So the check is this. What if the homotopy class theta in X is a pure loop in both U and V? What if it is a pure loop in both? Because it is conceivable, like let's return back to our picture. So if we return back to our picture, Here we have a loop. Okay, that's a loop. That loop is sitting both in V and in U. Okay, it's sitting in both. Then how do we define it? Another possibility that might come up is anytime we have a homotopy class, it can be represented in multiple ways. So maybe we can choose one representative, and this representative is a pure loop in U, but maybe we can find another representative where it's also a pure loop in V. So this is a homotopy class, so you have a choice of a representative, which one you want to use. And the point is, maybe by using one representative, it's a pure loop in U, or maybe another representative is a pure loop in V. So which one do you use? Then you have choices, right? You have to make choices. We saw that if it's only contained in one of them, then there's no choice. It's clear how you define H. But what if it's contained in both? So what we're going to argue is it does not matter. Then, regardless of which of the two choices we use, which of the two choices we use, it would not matter. Why not? Because let's return back to this diagram. Let's say that this loop is a pure loop both in U and in V. So then we can also find an element. We can also find a homotopy class of theta in V that will get sent to this one. So we can find two of them that get sent to it. And we have to argue, so we argue that you get the same thing. So we need to show, in this case, in this situation, we need to show that if you do K applied to theta of U, that would be the same thing as L applied to theta of V in the situation where theta is a pure loop sitting both in U and in V. So in other words, in their intersection. It is sitting inside their intersection. And the argument is very nice. It's very simple, but it's very nice because it is so simple. You would think it's something complicated. It's actually very simple. If it happens to be sitting in both, then you can pull it back even further. That's the point. You can pull it back even further. So then theta of U intersect V, this is then a loop sitting inside the intersection. That's a homotopy class sitting inside the intersection. And this homotopy class is being mapped to that one, and this homotopy class is being mapped to that one. And now look at how nice this argument goes. That if you want to go along K, right, if you want to apply K to this one, that's the same thing as first going by I star and then going by K. So then this one would be, this would be K of I star of theta of U intersect V. And this one would be L of J star of theta U intersect V, right? So if it happens to be a pure loop in both of them, then that means you can find a homotopy class that maps to both of them by these two homomorphisms I star and J star. So then you can express this one using that one, and you can express this one using that one. So why do they give us the same answer? Now, by assumption, so this is the part that's actually quite simple, but it's nice because it's so simple. So by assumption, H with its map. So it's not just H, it's also the maps with its morphisms. Commutes with the diagram that we started with. So this was the diagram that we started with. So thus, K composed I star is the same thing as L composed J star. That is just the assumption on the H. If we go back to the very top of the proof, so let's go back to this top of the proof where we had, right? So we said that to show that the fundamental group is the push out of this diagram, we need to show that if we can find another group, which is a push out of the diagram. So a push out of the diagram means it, by definition, commutes with the diagram, with the red diagram. And we have to show that the fundamental group is the optimal push out. It is the supremum of all of the push outs that you have. So therefore, so that's why this works. So if it happens to be both, then it works. So we have explained how to define, so we have explained how this homomorphism is being defined. And also, the reason why H is a homomorphism is because it's a composition of other homomorphisms, right? So H, right? So this is a homomorphism and that is a homomorphism. So H is being defined in terms of other homomorphisms. So the reason why you know it's a homomorphism, that is actually quite simple. It's just the fact that K and H are homomorphisms. But the part that is more subtle is how the H is actually defined. Not to check it's a homomorphism. It's being defined in terms of K and L. So we pick a homotopy class and we say if this homotopy class is a pure class, it comes either from this one or it comes from this one. If it comes from this one, then we define H of this to just be the image of that by using K. If it comes from the other one, then we define H of this class to be L applied to this one. If it happens to come to both, it does not matter because the commutative diagram will tell us that both of them send it to the same element in H. Okay, so that's sort of like step one. So we have explained how to define this when it is a pure loop. But what if it is not the pure loop? So that's the next step. So this is sort of step one. So I'm going to clear all of this because it's going to get in the way. And I want to sort of explain what we did. So let's redraw this picture again. We have pi 1 u intersect v. We have this thing I star, pi 1 of u. We are again suppressing the base points, pi 1 of v. This is pi 1 of x. This is j star. This is I prime star, j prime star. So we have this kind of diagram. And we want to show that pi 1 of x is the fundamental group. To accomplish this, we said that we're going to create an arbitrary group. This group has nothing to do with topology. This is just an arbitrary group. I'm going to assume that we have a mapping, which we call K, and we have another mapping called L. And K and L, they commute with this diagram. And we want to construct a map from the fundamental group into H. We want to construct a fundamental from the fundamental group into H. Let's call this H, lowercase h. That will make the diagram commute. So H will therefore commute. So if you go like this and then like this will give you the same thing. And if you go like this and then like that will give you the same thing. So we have constructed, so we have explained, so we have explained how to construct this mapping H in the special case when the homotopy class, so we pick an element in the fundamental group in the special case, and we defined how it gets mapped. So we have explained how to map it. And we saw that this H commutes with the diagram basically by construction, because the way we define it is we pull it back either here or pull it back either here by using these two maps, and then we define H by following either this arrow or that arrow. So H therefore commutes with the diagram by construction. We're forcing it to be like that. We have no other choice. Okay, so we defined in the special case when theta, so this is a loop in X, is a pure loop. So it is contained. So that would mean that theta is actually a mapping. There's a smaller codomain, either U or V, right? So one of these two happens. So we've defined it in this special case. But what about more generally? Because we saw pictures, so let's draw this picture again, that here's U, here's V, here is our base point, and here is a closed loop that is not sitting in neither those two open sets entirely. So this situation might happen. So what do we do in that situation? So what do we do in that situation? So what happens more generally if theta is not a pure loop. So then the idea is we can write theta as a juxtaposition of pure loops. So that's what we're going to do. We can sort of simplify it into pure loops. So how does one do that? So here's the idea. Since the interval from 0 to 1 is compact, we can decompose, we can partition the interval 0, 1 into subintervals ti minus 1 ti. So let's draw a picture. Okay, so this picture will be helpful. I'm going to draw this picture. Here's the number 0. So here's the number 0. Here's the number 1. And the first point is going to be t. So these are different time increments. This is t0. It does not have to be equally spaced, but it really does not matter. Right? Kind of break it up like this. The last one is tn. Yeah, so the last one is going to be tn. So this is for I between 1 and n. So you break it up into subintervals so that if you take theta and you restrict it to a subinterval, then this is a pure path in U or V. So notice we're not saying it's a loop. It is a path. It is a path. So now I am being a little bit sloppy over here. You see, I write over here, since the interval is compact. So details missing. There's details missing over here. We've actually done something very similar when we were defining winding numbers. We broke up our interval into smaller subintervals that had a certain desirable property. And we're doing the same thing here. We're breaking it into subintervals where a certain desirable property is satisfied. And I do not want to focus on that because that is not the main idea of the proof. The main idea of the proof is how to get those loops that we're after. That's really the main idea of the proof, not understanding how to break it up. So I'm being a little bit sloppy over here. We're just saying that since the interval is compact, you can achieve such a subdivision. And this is, of course, just general math advice that when you're writing a proof, you always want to focus on the main idea. That explaining how you subdivide it into those intervals, that's not the main idea. Maybe it would have perhaps been more appropriate to introduce a lemma in the beginning that explains why you can do it, and then we just reference the lemma in the middle of the proof. But then it would have been unclear why we're writing down such a lemma. So I'll just state it as a fact, and you can try to figure out why that is. It really has to do with compactness, and then you can try to figure out why that is. So since the interval is compact, you can break it up into pieces. So each of those subintervals, you can assume they're equally divided, but it really does not matter. If they're small enough, if the separation between them is small enough, then theta, so do not forget, so maybe I should just write this out over here. Theta is a mapping from the closed interval into your space X. And your space X is covered by these two open sets. By the way, you have to be very careful. We are not saying, we are at no point actually saying that X is compact. We're not saying that X is compact. We're saying this is compact. Compactness is being applied to this, not to X. It's true that this is an open covering of X, but if you take these two open sets and you pull them back using theta, then you get open subsets of 0, 1 that cover 0, 1 because these two cover X. And then you're applying the compactness on the pre-images of those open sets, of those open subsets of 0, 1. That's basically what you're doing. So we should not forget that theta is a mapping from that interval into X. And so when you restrict it to a smaller subinterval, it is not necessarily a closed path, because the only thing we know about theta is that 0 and 1 are being mapped to that point P. These intermediate points do not have to be mapped to that point P. They can be mapped somewhere else. So let's return back to our picture, and the picture will help us. And this picture is a little bit too far away. So let me redraw the picture down here. So let's redraw this picture down here. So how should we do it? So here's our picture. So we have x, we have, okay, so let's maybe, so maybe we should just, instead of calling it x, let's call this u, let's call this v. We have our base point, that's our point P, and then we have a closed loop that's going like this. So we're saying, so let's say that the orientation, for the sake of a picture, goes like this. So let's say that's the orientation on the loop. It starts at P, it goes around, it returns back to P. So we're saying that that you can subdivide this interval small enough so it starts at P, it moves somewhere. So let's say it moves up to here. So this one you can call T0. You can call this one T1. Okay, you can call that T1. And then the path from T0 to T1, as you can see, it's entirely contained. It's a path now. It's not a closed loop. It's a path. But it goes from T0 to T1. It's entirely contained in V. Then you might go from T1 to another point. Let's call it T2. From T1 to T2, right? From T1 to T2, and that one is also, well, you can also say it's contained. It's contained in V. And then if you go a little bit further, let's say all the way here, you have T3, and then when you come back, that's T4 again. So T4 in this case would be equal to T0. Again, I'm being very sloppy over here. I'm not actually saying that T0 is equal to Tn. What I really mean to say is theta of T0 is equal to theta of Tn. So this is not actually the value of time. That's the position on the loop at a certain moment in time. That's really what that's supposed to represent. Maybe we should get rid of this base point, or maybe keep it. Yeah. So this is what we have. And what we will do next is we will now construct. So since U and V are path connected, so this is where the path connectedness is being used. In the statement of the theorem, perhaps you forgot because we were not talking about this, but in the statement of the theorem, the assumption was that U, V, and the intersection were all path connected spaces. So that will imply that somewhere in the course of the proof, we have to use path connectedness somewhere. And this is where it's being used. So since U and V are path connected, let me take this down. I want to say something else. So note that let me do this. So let's define. So define theta I, or maybe not call it theta I, maybe call it Fi. So let's define Fi to be theta. We're going to take an affine map from Ti minus 1 to Ti. We're going to rescale it to 0, 1, and then we're going to recompose with theta. This is just a common thing we've done before, is we basically want to say that if you take theta and you restrict it to that interval, you're getting a path. But the definition of the path is a little bit annoying because it always has to go from 0 to 1. So all we do is we just rescale this, and we're going to call Fi to be theta applied to that rescaled version. So now by definition, these are paths. We define these. So F1, F2, Fn are pure paths. These are pure paths. They're entirely contained in one or the other. Okay? And so let's say it like this. F1 is a path from P. So from P to, so where does it stop? So this is sort of like the first one, right? This is the first one, F1. F1 goes like this. That's the first one. So F1 is a path from P. So we should not say T1, but really theta of T1. Or theta of T1, you see T1 is being rescaled to 1. So F1 is a path from, F1 is a path from P, which is another way of saying F1 of 0 to F1 of 1. So at time 0, you start at P. At time 1, because you've rescaled everything, that's really T1, you end up over here. So it's a path from, this is P, by the way. So this one is P, but this one is not necessarily P. and then F2, and then F2 is a path from F1 of 1 to F2. I'm sorry, F2 of 0. F2 of 0 to F2 of 1. So in general, right, so in general, Fi is a path from, maybe we can even emphasize it's a pure path, is a pure path from Fi of 0 to Fi of 1. Okay, now how do we get out of here? Okay, furthermore, okay, let's also add this. Furthermore, the entire path theta, it is the juxtaposition of all of those paths. So you have to be a little bit careful. You have to really write homotopic to, because the formula for the juxtapositions might be like rescaled and everything. So the technicality here is really homotopic to. So theta is going to be homotopic to the juxtaposition of these paths. And this is a homotopy, of course, in X, right? So this is a homotopy. This is a homotopy in X. So what, there's a continuous deformation from this one to this one, and the continuous deformation takes place in X. That's the entire space. Okay, so we have this, because this just follows from the fact that we've decomposed the entire loop into these smaller pieces. Now the issue is, these themselves are not closed loops. You see, we were saying earlier, so this is the idea. So let's go back to the very beginning. We asked, what happens more generally if theta is not a pure loop? And the idea is that we can write theta as a juxtaposition of pure loops. At the moment, we've written it as a juxtaposition of pure paths, but those are not necessarily pure loops. The way you make the way you introduce loops is simply by backtracking. That's basically what you do. You just go backwards. So let's look at this F1. You see this F1? It goes from this point to that point. And what we can do is we can just connect it by another path. That's all. And now if you go from F1 to, if you go to T1 and then you go back to P, you have just created a loop, and that loop sits in V. Okay, so here's what we're going to do. So we're going to construct a pure path, and this is possible. So by assumption, since by assumption U and V are path connected. So this is why this is important. This is where we're using the fact that U and V are path connected. So we're going to construct a pure path. Let's call it GI, which goes backwards. So this one goes from this Fi, this F1, it goes from F1 of 0 to F1 of 1. But this one's going to go backwards, which it goes from Fi of 1 to Fi of 0. So it just depends where each of these paths are located. If the Fi path is located in U, then this GI is chosen as a path in U. If this Fi path is contained in V, then the GI path is chosen as a path in V. This is why you need both U and V to be path connected, because you do not necessarily know which one of these is in which of the two open sets. So knowing that both of the open sets are path connected means that you can always construct a pure path that sits in the appropriate open set. Okay, and then if you do F1 Fi composed GI, then this is a closed loop at P. So actually, that's not good. I want it to be a closed loop at P, so that's not going to work. So let me change it. That's not correct. Okay, so construct a pure path. Okay, so we're going to construct a pure path. U and V are path connected, and GI goes from the base point. Okay, here I got it. It goes from the base point P to Fi of 0. And I think this should be Fi of 1. Fi of 1. So let's see the picture. So I made a mistake. No, this is actually fine. We have this path G1, it goes from P to T1, but the next path is going to go like this. It's going to go from, it's going to go like this, and then going to go, so all of them, because you want all of them to start at P. That's because that's sort of like our main base point, so they all have to go from, this point is common to both of them, and you can construct a path. So we therefore have a pure path that goes from P to Fi of 1, wherever that is. And then it means that if we return back to this juxtaposition, here's the way we can write it. So here's how it goes. So it goes F1, let's write star G1 reverse. It has to be reverse, okay? So let's explain why that is. So this first path, it goes from P to F1 of 1, right? That's the way it goes. So this path, we want it to, it goes from P to F1. So the reverse path goes backwards. It goes from F1 of 1 to P. And then the next one, we're going to write G1. We're going to put G1. G1 will now go from, so the next one will now go from P to F1 of 1. Okay, so we have that. And then we can juxtapose F2, because F2 begins where F1 ends. So this one is going from F1, it's F2 of 0 to F2 of 1. But F2 of 0 is F1 of 1. So those are the same. It begins where the other one ends. And then we juxtapose G2. We need a little bit more space here. And we'll juxtapose G2 reverse. So G2 reverse would then go from F2 1 to P, and so on, and so forth, right? And so forth. Then we juxtapose G2, juxtapose, so on, and then until we reach the very last one, which is going to be Fn. I guess it should be Gn juxtapose Fn. So this is the way we write all of this. And now we're going to introduce some brackets. Let's put brackets like this. Let's put a bracket like that. Now look at this. So this is the really cool part. This is going from P to F1 of P, and this one is going from F1 of P to P. So when you put the bracket in here, this thing is now a closed loop because it goes from P to P. This is now a closed loop. This one is going from P to F1 of P, and this one is going from F1 of P to F2 of P. So really, I guess this one the bracket should have went like this. That's the way the bracket goes. So notice how nice this is, because P goes to F1 of P. Okay, now F1 of P is F2 of 0. So F2 of 0, I meant to say F1 of 1. F1 of 1 is F2 of 0, right? This one ends where this one begins. That's the next one in the sequence. This one goes from F2 of 0 to F2 of 1, but then by construction, this is a path that goes from F2 of 1 to P, okay? So these go together, okay? And then this process, it sort of continues, right? It kind of continues this way. And so what do we have? So let's just summarize what we have. So this is a pure path. This is a pure path at P, a pure loop at P. This is a pure loop at P, and so on, and so are those. So, and for lack of a better name, let's just call this theta. Let's just make sure this is not in conflict. Yeah, that's not in conflict with anything. The reason why we have to go through this procedure is because the fundamental group uses loops. It does not use paths, so be very careful about that. The fundamental group does not use path. It uses loops. So you have theta 1, this is theta 2, this is, and then whatever the last one is, that's theta n. So thus, the theta that we started with, it's homotopic to theta 1 juxtapose theta 2 juxtapose theta n. So why is this, by the way? Why does this happen? Well, here's the reason why it happens. You see you have G1 reverse and G1. This is a result that if you take the reversal path and you take the path and you juxtapose them together, by the associative law, it does not matter how you bracket. So if you were to bracket these first, that's going to give you the identity. That's the identity. Well, yeah, that's the constant loop That's the constant loop at P. This one, the reversal path and G2, if you were to juxtapose these together, that would be the identity path. So the whole point is, by introducing these paths and their reversals, we're not changing the homotopy at all. So basically what we did is we argued that theta is homotopic to this just juxtaposition. And then in between F1, F2, and Fn, we introduced these extra factors, if you want to call them, but technically these extra paths. But these paths are coming in pairs. For every path, you also introduce the reversal path. So they nicely cancel each other together in a very nice way. So you're not changing the homotopy of theta. So the homotopy will remain the same. And furthermore, each of these are pure loops by construction. Every single one of them is now a pure loop. So you have, therefore, written theta in this way. Right? Theta is now written in this way. Okay? So therefore, the homotopy of theta in X is equal to the homotopy of theta 1 juxtapose theta 2 juxtapose theta n in X. But this is therefore equal to the product, because the product of loops is, by definition, the juxtaposition. Okay, so now how do we define H? So how do we define H? So remember what H is. H is our homomorphism from the fundamental group into this arbitrary group H, which is a push out for our diagram. So we have picked a element in the fundamental group. This is an element in the fundamental group. And we have taken that element in the fundamental group and we have factored it as a product of pure loops. So how do we define it? So then we are forced, so notice this, we are forced to define H of theta x. So this would be H of the product of these pure loops, theta n x. We are forced to define, maybe to add, since H is a homomorphism. Since H is a homomorphism. So since H is a homomorphism, H applied to a product, by definition of a homomorphism, is the product of all of those. So it's equal to H of theta 1 of x, H of theta 2 of x, H of theta n of x. So it's equal to all of those. But these homotopy classes are pure loop classes. And we already know how to define theta, how to define this, okay, from before. So that's the discussion that we had previously. So our previous discussion explains how to map these. So therefore, here's the way this mapping H is defined. You pick a loop in the fundamental group. You take that loop and you can factor it as a product of pure loops. And then you define H of this homotopy class of this loop to be the mappings of all of these pure loops. And how do you define the mapping of the pure loops? That's what we did previously. That's the one that comes from the commutative diagram. Okay? So we see from here, so to conclude, H is a homomorphism from pi 1 xp into H. Why is it a homomorphism? Well, because you see, H of this is equal to H of that. And if it is a homomorphism, then H of that has to be this. You have no other choice, right? It has to be that. It just has to be equal to that, right? If it's a homomorphism, that is forced on you. And then, how is H defined? Right? So to conclude, H is a homomorphism by construction. So there's two steps here. The first step, where you factor it as a product, H of the product is the product of these factors. That's the homomorphism, so by construction. And then H of all of these, which are the pure loops, that one was defined from the commutative diagram by using either the K mapping or the L mapping, if you recall, which were homomorphisms themselves. So H is a homomorphism by construction. Furthermore, h from pi 1x in p into h is unique. There's only one way to do it, since our definition for h was forced to satisfy the commutative diagram and the homomorphism property. So the homomorphism property and the fact that it has to commute with the diagram forces h upon us. There's no other way to do it. So it's unique. And then finally, h commutes with the entire diagram, by construction, for the same reason as before. When we defined it on the pure loops, we just followed the diagram. So by construction, it commutes with the diagram. And so pi 1xp satisfies the universal property for the pushout. So we showed that this is the optimal pushout. So pi 1u intersect v comma p, going into pi 1u comma p, going into pi 1 v comma p, that the optimal pushout, the optimal way of pushing this out, is by using the full entire fundamental group of the entire space. If you put that into this diagram, that is the optimal pushout. It's optimal in the sense, if you have any other pushout h that is compatible with the diagram, then there's a unique mapping from the fundamental group into h that is also compatible with the whole diagram. So this is the optimal. That's sort of the supremum. That's sort of like the least upper bound out of all possible pushouts. So that verifies the claim that the fundamental group is the pushout. Now there is, however, one detail. So there is one detail in this proof that is overlooked, and it needs to be addressed to have a fully complete proof. And an exercise for you is to figure out what this missing detail is. What is missing detail in this proof? So the proof is correct. Okay? This is not like the proof that we gave for the fundamental theorem of algebra, which actually had a minor flaw in it, if you happen to figure that one out. So this proof is actually correct, but it is missing something. There's something in the proof that should have been mentioned, but we do not mention it. So see if you can figure it out. And by the way, let me make a comment. You might have noticed that we used the assumption that u and v were path connected in this proof. However, mysteriously, u intersect v being path connected was not used anywhere in the proof. You can kind of go back to it. You will see that we only needed the fact that u and v were path connected. We did not need that u intersect v was path connected also. So this is actually used. This is used in order to address the missing technicality. There's a missing technicality I do not want to get into. It's very boring. It's not very interesting. It's very long. If you thought this proof was long, well, take this proof and multiply it by a factor of 4. Like at some point, it just gets too excessive. And if you really want to understand it, you just learn it. So I will give you a reference that I think is better. Right? This is a better reference. So something I think the following proof is better. You can look at, I think it's called a first course in algebraic topology by Massey. So this is a GTM book. I'm actually not sure. He has 2 books. I have to be careful. I'm not sure which book it is. I think there's like a first course in algebraic topology, and then he has another book called, I think, an introduction to algebraic topology. I'm not actually sure what the difference between the 2 books are, but it's one of those 2 books by Massey. It's a graduate text in mathematics. It's around page 90, 85 or 90, something like that, somewhere in that neighborhood. So if you pick up the correct book, then that's somewhere where it's located, somewhere in the neighborhood of that. And I think Massey has a nicer exposition than Moncrief's. My criticism with Moncrief's is I like his book very much. I think it's a great book. My only criticism with the book is that it is unnecessarily wordy. Some of his arguments are way too long. And writing out so much details is sometimes counterproductive because every proof contains a main idea. There's always that main idea in the proof. And if you look at what Moncrief does with this proof that we did right here, you're not going to, it's much harder to see that the main idea of why this works is in the way that we explained it. That's sort of the main idea. And then there's that technicality that we did not mention that has to be addressed. So that's sort of like the missing part here. Now, I want to mention something interesting before we go. So this is like a great exercise. So here's like a fantastic exercise that I'm going to put on the homework, and you can do this yourself. So suppose P is in X and Y is in Y. Okay, these are two spaces. And let P be the product space, of X and Y. So if you want to be very concrete, you would just say that P is the product of those two, right? That's what you would say. But you put the Cartesian product, then you define the topology on the Cartesian product. But I want to treat this exercise a little bit more abstractly. So let P be the product space of X and Y. So let's draw a picture. So a product space means that you have a map. It's similar to a coproduct, but it goes back down. And you have a point in X and you have a point in Y, okay? And since this is a product space, so let's call it Z be the unique point in P which projects to P and Q. So whenever you have a product space, you have two mappings. We call them the projection mappings because that's the way we do it in the construction. But in general, they're just mapping. So i.e. pi x of z is P and pi x of z is Q. So prove, okay, so now let's apply the fundamental group. So thus, if you take the fundamental group of P at Z, that goes to the fundamental group. Okay, this is really funny. We have really funny. It's unintentional. I did not even realize it until now. Overloading, right? Overloading. Pi x and pi 1. Let's keep it because it's funny. Okay, it's funny. We have two different pi's, fundamental group and the projection map. So let's just keep it like that. I'm sure you can tell them apart. So pi 1 of x p, and this one is pi 1 of y q. So look at that. We have a group that projects to those two. So you can suspect, is this group the product of those two? And the exercise is prove that pi 1 of p at this point z is the product group of pi 1x p and pi 1y and pi 1yq. You prove this. So this is what you're going to prove. It's a nice exercise because you are reinforcing these abstract definitions of products and coproducts, products for topological basis, products for groups, and all of that. It is possible to prove this in a more concrete way. So let me make a comment here. So you have a corollary. So let me tell you a corollary. So the corollary here is if you take pi 1, if you take the product space in a very concrete way where you construct it as a Cartesian product at the point P comma Q, so that's the point that is in the product space, then the fundamental group of the product space is going to be isomorphic to the fundamental group of X at P and then times the fundamental group of Y at Q. So we'll have that kind of relationship that happens when we do this. So this is the relationship. Yeah, so this is going to be the relationship that we will get. Okay, so it is possible to prove this. So you can prove this more directly by thinking of elements and sets and constructing isomorphisms. It's not difficult, but not as elegant. You can find it in Moncrief. So Moncrief does it like that. So Moncrief thinks of the product space in a less abstract way as a Cartesian product with a certain topology, and he thinks of the product group also as a Cartesian product with a certain group structure, and he shows that you have an isomorphism. It's not particularly difficult to do it this way, but I think it would be more fun to try to use this definition of the product space and all of that to show that this satisfies the universal property for the group product. So that's like, I mean, it's nice for modern mathematics. Like in modern mathematics, we often like to think in terms of universal properties. So this will be like an excellent chance to practice this. It's a little bit similar to what we were doing with the push out, but it's a lot easier. This one is not, like the one with the push out is like substantially harder to prove. This one is much more straightforward. So this is great. We have discussed how to compute the fundamental group by using the Seifert-von Kampen theorem. We discussed the theorem. We gave almost a complete proof with a missing technicality. And next time we will start showing how you can use the Seifert-von Kampen theorem to start computing fundamental groups of various spaces. So that's going to be very exciting. So we finally get to see how all of this comes together.